Hello, everyone, and welcome to today's webinar, EV Battery Opportunities for Converters. I'm Jim Brzaitis, the Marcom Manager for Performance Tapes in North America, and I'll be your moderator today. For clarity, all the audio lines will be muted during the presentation. So to submit a question, use the question and answer tool located on your screen. Time permitting at the end, we'll try to get to all the questions. If your question isn't answered, we do have your contact information. We'll get back to you directly, provide an answer. Our presenters today are Avery Dennison, Performance Tapes Automotive Business Development Manager, Mike Van Herens, and our Automotive Product Manager, Scott Krasinski. So we're gonna get started. I'm gonna hand over to Mike to get us started on today's venture.
Thanks a lot, Jim. We're gonna cover here on our agenda today, automotive EV market conditions and trends, supply chain and the converter's role, pain points and common challenges, some different EV battery applications, and how we're going to address those with our portfolio of products. And then finally, as Jim mentioned, question and answers at the end. Hey, Scott, do you want to tell us about Automotive Trends?
Yeah, sure. Thanks, Mike. So over the course of the 2020s, we do expect some strong automotive trends to occur. The big leading trend is electrification. And the idea behind electrification is that your car is essentially becoming a big electronic device. And there's smaller trends under electrification that are occurring to create this bigger trend. So the first trend worth noting today is obviously battery propulsion. Lithium-ion battery cells are taking the place of internal combustion engines as a way to propel your vehicle. We expect a strong growth curve of EV batteries taking over the market, and Mike will go into that in a little more detail here soon. Another big trend is ADAS, or Advanced Driver Assistance Systems. This is the inclusion of sensors and cameras and computers to help the driver drive. So it could be as simple as a lane departure warning camera that will beep at you when you are veering off of your lane, or it could be more detailed, such as collision avoidance systems that will actually, the car will proactively brake for you if you are in danger of colliding with another vehicle. And then the furthest extent of ADAS would be fully autonomous vehicles. And we still have a ways to go before we see all cars becoming fully autonomous, but we are seeing some OEMs introducing some type of version of autonomy in their latest vehicles. Another trend within electrification is the further adoption of electronics and digital integration. So we're seeing touchscreens as the center console, and they keep getting bigger and are expanding across the entire dashboard. We see further digital integration with your phone, with Bluetooth, and just more smart devices being incorporated in the car. Adjacent to the electrification trend is improved comfort and user experience. So the inside of the car is changing along with the electrification. There might be fancy features like lighting that make a cooler user experience that are being introduced, but then also an emphasis on improved comfort. And that could be things like there's more seat heaters being used in chairs, including the back chairs, along with your steering wheel is actually, some of them are being heated up, which is a nice little luxurious thing in the winter. Another trend that's been ongoing for the last 30 years or so and is still continuing is lightweighting. Heavy fasteners and other metal materials are being substituted for plastics and foams and gaskets. And then a trend that is really strong in North America, especially with the United States, is the fact that consumers really prefer SUVs and trucks. And those are expected to take larger share with this decade. And you see some OEMs actually downplaying their sedan offerings. So these are the trends for the 2020s. What kind of impacts does that have on the converting and tape industries, Mike?
Yeah, so how will these trends impact the tape and converting industries? So just starting to look at emerging applications. We have 5 of them listed here. Battery pack materials. We have EV battery packs with many different applications for tape, as well as flexible and functional materials, such as polyurethane foams and compression pads. We're going to cover these a little bit later in the presentation. ADAS, which Scott had mentioned already. We have sensors and camera systems. Our acrylic foam bonding tapes are excellent for bonding the polycarbonate camera housings. And because they're non-metallic, they also work great for radar and LiDAR applications as well. Acoustically insulated tires. This is a new emerging space. Sounds that were normally covered up by engine noise are now causing issues for electric vehicle OEMs. Tires is one of the big areas of noise in a vehicle. Bonding acoustically absorbent foams with tape inside the tires can help reduce that noise. We have touch screens and user interface. Obviously, anyone's looked at a vehicle recently will see the ever larger sizes of touch screens becoming more prevalent, and that offers a lot of opportunities for tape. Things like lens bonding and mounting, where the liquid applied products have issues with runs during assembly. And that's not a technical term, but it's what I'm going to use here today. Steering wheel hands-off detection for ADAS. These detection sensors are very prevalent for level 2 autonomy and beyond. Anyone who's seen pictures of or photos of bricks hanging from steering wheels, simulating a human behind the wheel, that's not going to cut it in the future. Steering wheel feedback force, which is one of the items used today, it's not going to be sufficient for government regulation in the near future. Next slide. All right. So then we have existing and growth applications. All right. So Scott already mentioned seat and steering wheel heating and seat ventilation. We also have foam and fiber bonding and buzz, squeak, and rattle. We talked about the lack of white noise from the engine within the cabin. This is going to be increasingly gaining popularity in application. Flexible printed circuit bonding continues to grow with those larger touch screens and instrument clusters to make those electrical connections. And airbag wraps and adhering other occupancy sensors for safety. Next slide. So I got a lot of statistics here, and just bear with me. I'm going to try and go through these as cleanly as possible. But the future of global electric vehicle demand, and we'll share this with everyone afterward, but electric vehicles are expected to rise from just a 2.6% share in 2020 to 25.7% share in 2030. And some of the things highlighted also here, we got a 36% CAGR from 2021 to 2025 of EV-related battery components, and that's going to be capturing 28% of the light vehicle by 2025. And then we have charging components separate from the vehicle itself, and it's going to grow at over a 26% CAGR through 2030, and that is expected to exceed over $150 billion in top-line sales. So moving into the 4 drivers here we have listed, battery technology continues to improve capacity and range. Things like lithium iron phosphate batteries offer greater range than traditional cobalt-containing lithium-ion batteries, and that's going to keep driving that range and adoption rate. We also have, probably in the next decade, solid-state batteries on the horizon for the future, both in consumer electronics and then making their ways into transportation and light vehicles. We have increased OEM investment and goals. Major automakers continue to talk about and make investments in cell manufacturing, and then announcing ending investments with internal combustion engine development. For example, Audi, I believe, has announced that in 2026, they're going to stop doing any further internal combustion engine development. Third, we have falling battery costs. We're going below the threshold of $100 per kilowatt hour. And that's a very important threshold. For those of you who don't know, years ago, our North American, United States Department of Energy theorized that this was the break-even point between internal combustion engine and EV powertrain adoption, and we're there now. Policy and emission regulations, we're going to talk a lot about that on the next slide. So implications. EV battery packs have needs that need to be addressed by tapes and flexible functional materials, and this represents a tremendous opportunity for converters. There's much more tape being used today on electric vehicle batteries than there are on traditional internal combustion engine powertrains. So here we have a map of a lot of different internal combustion phase out years across the globe. So what's driving this? Well, we talked a little bit about this on the last slide, but we're going to talk about policy here. You know, we have global CO2 emission policy as being one of the major motivators driving this initial growth. So starting here in North America, the Biden administration talked about the new Green Deal environmental plan of executive orders. And as part of that, it promised by 2030, we were going to have 500,000 charging units nationwide. That's up from an estimated 90,000 we have today. We have the US government fleet of over 650,000 vehicles, potentially going all electric during that time. And then we also have our Department of Energy here in the United States pushing for US sourced rare earth minerals. And that's going to strategically shore up both our domestic supply of those materials while also giving us less reliance on foreign importation of those materials for lithium-ion battery packs. Then moving over to the European Union, in 2020, they announced very aggressive CO2 regulations that basically require about a 57 mile per gallon efficiency rate of all new vehicles sold after 2020. So what does that mean? Well, all of the European Union is potentially moving towards an ICE engine ban by 2030 potentially. And then I'm just going to finally highlight just a few of these on this map. Obviously, everyone can see it here, but we have California announcing an ICE engine ban on light vehicles by 2035. Washington proposing a ban in 2030. British Columbia and Canada by 2040, and Massachusetts in 2030. And then you have also two automakers that have announced General Motors going all electric by 2035 and Volvo going by 2030. So huge developments in this side. So on the next slide, Scott's going to tell us more about navigating the supply chain.
Okay, so the EV battery supply chain can actually be quite complex, and there's varying degrees of vertical integration going on between the cell manufacturers and the OEMs. For today, we're going to oversimplify the process and discuss the pack supply chain and then talk about how we fit in the supply chain. So the battery pack supply chain begins with cell production. There are cell producers that are producing typically 3 different types of cells, and Mike will talk about those cells in a second. These cells are assembled together into a module. There's probably 10 or so amount of cells that go into a module. A module is almost like a mini battery pack in some ways. And then these modules can be assembled together within the overall battery pack. And there could be about 10 or so modules per battery pack. So just think about the amount of interfacial surface area that's going on there. You have the surface area of the cells, of the modules, and the pack. And there's an opportunity for materials to be placed in between all of those nooks and crannies. And that's where we come in as a tape and converting industry. So obviously there's functional materials that can be used like foams, films, and fibers that are solving some challenges within the battery pack. Those materials often need to be laminated to a pressure sensitive adhesive tape. And that's where the converter comes in. They can laminate and die cut these materials. And these types of solutions can enter the supply chain at various points. So films and tapes and some other materials are used within the cell production, but then also on the outside of cells. These materials could also enter into the module level. So maybe they're going in between the cells or along the module walls, or at the pack level where they could be fitting between the modules or as part of the battery pack walls. So as we'll discuss today, there are many applications, and we'll talk about those different materials in a second. So what is the converter's role? So converters are going to play an essential role in the EV battery supply chain. By working hand in hand with Avery Dennison, converters can assist functional material suppliers, battery pack manufacturers, and OEMs in several ways. First of all, in Obviously, they can laminate a wide range of materials. And some of these materials are going to be more exotic than your traditional automotive interior material. So things like mica or ceramic paper or blankets and some dielectric films can be laminated to Avery Dennison tape constructions. Converters can create multi-layer composites that integrate multiple functional purposes. So whenever you're able to incorporate multiple functions within a small, thin composite, you are saving space and solving challenges for pack manufacturers. Of course, converters are die cutting to custom shapes, and they can create part presentations and provide consultation to facilitate automation of these parts for assembly via kiss cutting, dispensing, and having extended liners. And then finally, of course, they can provide quick prototypes and samples when OEMs need them. So let's get into the EV battery pain points and common challenges, and I'll hand it over to Mike to discuss OEM and customer pain points.
Thanks, Scott. So I guess within OEM and customer pain points, right, you have, they both have similar goals, but they express them in different ways. So we've charted out some common ones here between the OEMs and the end customer. So on the OEM side, you have 5 basic ones. You have safety, durability, functionality, production efficiency, and cost. So starting with safety, you have things like thermal runaway and fire, electrical arc and short protection, impact protection and crash survival, cell protection within itself, and vibration protection of thermal materials. With durability, you're basically trying to stop corrosion within the pack. So whether that's from oxidizing corrosion protection from aluminum and steel components, or whether that's galvanic corrosion of dissimilar metals. Within the functionality side, we have range efficiency, pack cooling during charging, and that also goes along with heat dissipation, both during operating and during charging, to allow for, you know, those really fast starts of your vehicle or very quick charging of that vehicle when it's empty. Production efficiency, well, your OEMs are always looking to improve throughput of their manufacturing operation, and cost, right? Cost is always an ever-present driver. So with the end customer, their goals are very similar, but expressed in different ways. We have safety from the thermal runaway and fire, impact protection, and crash survival. Range, we all want acceptable range of our electric vehicles to reduce the range anxiety. And along with that, you know, charging times. As quickly as we can charge that vehicle, we want it to be able to be used. And when you're looking for a charger, we need charging infrastructure availability too. And then finally, we as consumers always are looking for the lowest cost possible. So on the next slide, we're going to cover here our cell types and a little bit of what I like to say is EV battery 101. So we have 3 basic cells. Scott kind of made mention of these earlier in his slide, but we have the cylindrical cells in the upper right. It was the original cell style, cylindrical in shape, low packaging density, and the interconnections can be very complex and many interconnections, but it was an existing technology and existing form factor. From there, we went on to prismatic cells, which is in the lower left picture here. And they're typically aluminum or steel cased rectangular cells that offer additional protection and a better fit. And then we've been evolving in some instances to a pouch cell, which is in the upper left. Pouch cells are basically metallicized polyester pouches, and they're very similar to what's inside that prismatic cell, just not with the casing that protects it. So Scott mentioned these traditionally go from a cell into a module and the modules into a pack, basically just turning many things into a smaller amount of things into one final thing, right? So that cell protection, kind of talked about this already, but we're trying to protect it from thermal energy, thermal transfer, and fire. We're having to retain that cell through adhesion, cell expansion, or shock absorption. And electrical, dielectric protection, protection from electromagnetics, especially with the sensors that exist within that pack, And then finally, environmental, protecting it from water and humidity and salt, all the stuff we talked about with corrosion from that pack. So on the next slide, Scott, do you want to tell us how our portfolio addresses these challenges?
Yeah, so the portfolio was designed to address these common challenges, and the common challenges that we're highlighting and focusing on are reducing flammability. We've talked a little bit about thermal runaway here, and just to clearly define it for you guys, thermal runaway is when one particular cell gets damaged and catches fire, and then like a domino effect can spread slowly to other cells one at a time. And that can create that larger fire that you sometimes see in the news there. So there are materials being used to mitigate that, and some of our products in this portfolio actually facilitate reducing flammability by incorporating flame retardants. And we're introducing a new line of product called Flame Tough that we're very excited about. Another challenge that we're addressing here with this portfolio is boosting dielectric strength. Mike was talking about the electricity that's flowing through the pack and how there's a need for electrical insulation. And then also protecting pack materials. And we'll go into more detail with these on the incoming slides. So first up, how are we reducing flammability? So we have acrylic and silicone-based adhesives that have flame retardant properties that can allow composites to pass UL 9.4 requirements. So there's a variety of UL 9.4 actually here. So I'll quickly walk you through the different test modes here. The first one shown on the left there is UL 9.4 VTM. VTM stands for very thin material. So this could be like a film or a tape, for example. And how it's tested is that thin material is folded up like a cone. And at the base of the cone, the flame is put in the center. It doesn't actually technically make contact with that material, but that material can eventually catch fire. So the requirements from the test are that the flame is not allowed to spread a certain length and burn for a certain amount of time. And that's a consistent requirement across the different test methods. There just might be different requirements on the time and the length it can go. The middle is UL 9.4V. So this is for thicker composites that are tested in a vertical mode. So this could be a combination of a compression pad foam with adhesive and a film, and the flame is directly placed on the bottom of the material. This is a pretty challenging test because in a vertical mode, the flame can travel upwards very quickly. And then finally, a slightly easier version of the UL 9.4V is the UL 9.4 HBF, where the composite is tested in a horizontal mode. It's also very similar to the FMVSS 302 test that is quite common for other automotive applications. But here, the flame is connected directly on the side of the composite. And again, it's not allowed to burn for a certain amount of time and a certain distance. But the horizontal mode is a little easier than the vertical mode. So next, Mike will take us through dielectric testing.
All right, thanks, Scott. So insulating and protecting EV batteries, the second of the protection type properties here. EV battery materials typically have dielectric requirements associated with them. And we've seen anywhere from 2,000 volts to 4,000 volts DC of a requirement. Here we have a couple of depictions. On the left here, we have a high pot tester, which is how breakdown voltage and dielectric strength are typically measured. Avery Dennison offers full high pot testing of any of our single and double coated tapes we have in this space that incorporate the dielectric films. And on the right here, we have images that depict a couple different composite options. So on the left is a very traditional single coated type application. We have a dielectric film combined with a pressure sensitive tape on an aluminum substrate. And then on the right, we have a much more complex multi-layer composite consisting of either like a polyurethane or silicone foam compression pad combined with dielectric film and layers of PSA for adhesion. So on the next slide, we're going to talk a little bit about protection here on, in addition to the dielectric strength, we're going to protect those critical battery components from both the oxidizing and galvanic corrosion I spoke about a little earlier. Corrosion can really hinder electrical conductivity, heat transfer, and the structural integrity in really severe cases of those critical battery components. And these battery components are things like we have listed here, chiller and cold plates for pulling heat out of those cells, bus bars that interconnect the cells themselves for electrical conductivity, the aluminum castings for the battery modules, and then the aluminum or steel battery pack housing itself. So on the next slide, Scott's going to tell us about how we're going to protect those EV battery pack materials.
Yeah, so the portfolio will include single and double coated tapes that incorporate a filmic face stock or carrier. And these are important because it provides dimensional stability and material encapsulation for some of these materials. So you will learn a little bit more about thermal runaway mitigation materials. Some of these materials are fibrous and flaky and start dusting. So a filmic carrier or face stock coupled with an adhesive can actually help encapsulate that material, preventing that dusting from occurring along the assembly process, but also in the battery pack during end use. In addition to the carriers and face stocks, we have optimized release liners, so particularly easy release. Some of these materials are delicate and actually will tear when the liner is pulled away from it if it has a traditional release coating. So we've coated it with easy release liners so that the materials can dispense quite easily. Next, we will move on to applications here, and Mike will take us through all the applications.
All right. So we have 7 common applications we're going to cover here today. I know this has been a lot of information for you out in the audience to understand so far, and there's a lot of text on these slides, and I'm not going to go through it all for the sake of not losing you and trying to keep you entertained here as well. So we're going to cover, start with thermal runaway protection as the first application here. EV battery manufacturers have really strict requirements on thermal runaway events. Thermal runaway events of a cell catching fire and causing multiple cells to catch fire, and you can imagine very catastrophic event. So these exist both at the OEM level and then at the governmental level. In Europe, we have a UN GTR 20 phase 2 doctrine, and we also in China have GB standards that cover that. And then finally, we have the news media and the internet who loves to show pictures of burnt up electric vehicles. And that's just never good for sales, showing that. So we really want to stop that from happening as much as possible. So, how do we protect these cells? Well, Scott had already talked about some of these materials. We got mica and ceramics and phase change materials, as well as other composites to really protect them. So where does Avery Dennison come into play with all of this? As mentioned earlier, we have materials to bond these type of ceramics and micas to the cell's modular pack structures, depending on the construction type. They meet that UL94V standard, whether V0 or VTM0. And then we combine that with proprietary flame-resistant materials like our flame-resistant PETs or polyamides, typically known as Kapton by trade name, for fiber encapsulation and giving that dielectric strength. Next slide. So the next application we have is cell-to-cell bonding. And as the picture here depicts, we have a stack of prismatic cells here with adhesive between each one of them. Bonding these are like stacks of books on a bookshelf, right, with layers of PSA tape between them. Primarily used for prismatic cells in these EV battery pack assemblies. And like any PSA tape application, it requires no cure time. We have that immediate strength. It can act as both an assembly aid and a bonding solution. There's no need for mixing nozzles or pot life concerns, unlike a lot of the liquid applied products. And we can combine those with a flame retardant or a dielectric resistance if needed. So on the next slide, we're going to talk about compression pads. So compression pads are just an offshoot of cell-to-cell bonding, where we were looking at those prismatic cells stacked like books on a bookshelf previously. In this type of application, we're bonding compression pad foam, whether that's a polyurethane or silicone-based foam, in between those battery cells for protection. So, why are foams used in this type of space? Well, pouch cells can swell as much as 30% during their charging and discharging cycles, both from the time that they're new and then also as that cell ages. And the prismatic cells, even though they're encased in aluminum or steel casings, they still swell up to 5% as they age too. And this difference in thickness actually has to be made up by something, and these compression pad type materials are what allow it to do so. So individual prismatic and pouch cells and individual in EV battery packs need protection from this impact and movement. And to help prevent damage, EV battery manufacturers are placing these foams in between each of these cells. So on the next slide, we're going to get into a little bit of insulation, cell, and wrapping. We've talked a lot about dielectrics here. This is where it really comes into play. Both electrical insulation and cell wrapping are critical for protecting conductive components within that EV battery from arcing and shorting. We have both single and double coated tapes that incorporate these dielectric films, as Scott has talked about already, where double coated tapes are typically combined with other materials such as the compression pads to achieve that electrical insulation and combining the adhesion. And then we have the single coated tapes that can be applied to things like rigid materials such as aluminum chiller plates or metal structures, aluminum steels, to protect them from dielectric or to give them dielectric strength to protect them from arcing and shorts. And then, so other options, we can always combine these with those flame retardant adhesives if you need dual dielectric and flame protection. And Scott, we've heard this a lot from our customers, that there's a need for more flexible dielectric materials. Can you tell us a little bit more about that?
Yeah, so as is a theme with our overall portfolio, this is just an initial portfolio, and it's a Gen 1 portfolio. We expect it to evolve and to introduce new products, and this is one area where we can introduce a new product. So if you think about Avery Dennison Corporation as a whole, we have a wide variety of films available to us from our graphics division, our labels division, and some of those films are more conformable than traditional polyester and polyimide film. So we are working on ways to incorporate those conformable films to kind of get into the nooks and crannies of irregular geometries. And if that sounds of interest to you, let us know, and we can collaborate on it together.
And I think one of the advantages that we have here too is that we do like to work with converters, and we work with the tiers and OEMs to really continue to evolve this portfolio. So it's not just a fixed portfolio of the products that we're going to be showing here and discussing today, but we're also evolving the portfolio based on those critical characteristics that people are telling us that they're in a need for. And that's kind of where this generation 2 of materials starts to develop from, is that feedback we've been getting from our customers. So the next slide, we're going to talk about flexible bus bars. So flexible bus bars is an application of that dielectric. They're of the electrical insulation tapes. They're used for both the high voltage, high current applications, as well as low voltage sensors and circuits, which is primarily more what we're seeing use of here today. They offer flexibility, safety, and cost effectiveness of the applications, allowing for more durable connections and flexibility in manufacturing. These flexible bus bars are obviously flexible, hence the name, but they really allow cells to be interconnected in a much simpler way versus traditional wire soldering or ultrasonic welding that's used in a lot of the cylindrical processes, or even some of the prismatic processes to hook up those together. So as discussed in the last slide, we offer tapes to protect these type of flexible printed circuits for both electrical insulation and flame resistance. Next, we have our thermal interface management materials. So, thermal interface management materials are used to transfer the heat between the battery cells or the modules and components that are designed to cool, such as chiller plates and within the EV battery. These thermal interface materials serve another function in addition to heat transfer. They also help fill tolerance gaps that exist between the cells and the terminals. The thermal interface materials have some very unique requirements when it comes to adhesives. We use very high wet out adhesives to lower the thermal impedance between the thermal interface material and the heat source. So what are these thermal interface materials themselves? I mean, Avery Dennison is a pressure sensitive adhesive manufacturer. We don't manufacture these TIMs themselves, we help bond them. So we typically see silicone-based materials, siliconized foams, and we have siliconized or silicone, pressure sensitive adhesives to bond these. And then when we have things like polyurethanes that are being used for these TIM materials, we have acrylic pressure sensitive adhesives that offer excellent bonding with very high wet out. So we can move on to the next slide here. Finally, our last application here, pack sealing and gasketing. So creating a tight seal of these components is critical in the construction of an EV battery assembly. You can't have any moisture, whether that's humidity or water condensation or anything within that battery pack. Obviously, electricity and water, anything that conducts, don't mix very well. So we offer our heat activated acrylic foam tapes to help maintain a watertight seal between the casing and rubber gaskets. And these rubber gaskets are typically profile extrusions that would then be bonded to our heat activated acrylic foam tapes. And that acrylic foam core helps assist in the gap filling between those rigid components, and then it gives you a continuous bond line to seal out unwanted intrusion and also reducing the need for fasteners. In some markets, for specific OEM manufacturers and the markets like I discussed, pack serviceability is a big issue. So this allows that pack to still be serviceable versus some of the other solutions that are out there today. So after this here, Scott's going to introduce our EV battery product portfolio.
Okay, so as you've learned from Mike, there are multiple applications, and by the way, there's other applications that we didn't even cover that have multiple needs and various requirements. Avery Dennison Performance Tapes has designed a first generation portfolio to address these applications with a wide range of products. So this includes single-coated, double-coated, and transfer tape constructions with a variety of liner options for optimized release and efficient processing. It includes acrylic and silicone adhesive chemistries with a range of performance for adhesion, shear, tack, and environmental resistance. And it also includes functional additives and films for specific EV battery component needs, such as flame retardants and dielectric films. So as we move deeper into the the portfolio here, it's divided as kind of like a mix and match situation. So we have certain adhesive categories that can be married with certain carrier and phase stock categories. So first up, we have a general automotive acrylic that is a tacky acrylic that is good for bonding to low surface energy materials, but still has excellent temperature resistance and durability. And it's used throughout the vehicle for things like foam and fiber bonding within the interior, but also for things like heat shields. Moving on to the next category, we have our high performance acrylic, or HPA. This is designed for high performance requirements such as high temperature and high shear. Back to HPA, excellent temperature resistance and shear resistance, and it's a great product for cell-to-cell bonding where high shear resistance is needed. The next category is one of the new categories that we're introducing with this portfolio with our flame tough acrylic. This is very similar to the general automotive acrylic, however, it has flame retardant properties. The next category we're introducing is the flame tough silicone. This is a silicone adhesive with flame retardant properties that has excellent temperature resistance and even better flame resistance than the flame tough acrylic. And then it also has the unique ability to bond to extra low surface energy materials like silicone-based foams. And then the final category for adhesives is our AFB. These are acrylic foam tapes that are designed for gap filling and bonding rigid components to each other. Then the carrier and face stock categories, we have a traditional polyester that has about 6 kilovolts per mil of dielectric strength. We are introducing a new flame tough polyester that has similar dielectric properties, but also the added benefit of flame retardant properties. And then we're also introducing a flame tough polyimide, which has even better dielectric strength and even better flame retardant properties. So next we'll show you how the products align with specific applications. So take, for example, the second category below, we have compression pad bonding. These are our go-to products for this particular application. And you can see there's about 9 or so products. There's about 4 transfer tapes and 5 or so double-coated tapes. And we list information about whether or not they have dielectric properties and flame retardant properties. But we can view our portfolio on a more holistic basis in the next slide here by showing you how they're grouped by adhesive category. So take, for example, the flame tough acrylic again. That's the middle category. There's about 6 or so products in there. There are 2 transfer tapes with that flame tough acrylic, 2 double coated products, and 2 single coated products. And here's where the mix and match comes into play. We have this coupled with our flame tough polyester and flame tough polyimide to make those unique constructions. And as you move along in the table, there's more information about the liner, the level of flame retardancy, the level of dielectric strength, and then other properties like low surface energy bonding. We have another cool product in here too that couples the flame tough silicone with the flame tough acrylic as a differential double coated tape. So if you're bonding a silicone based foam for compression pads, on one side the flame tough silicone can bond to it, and then on the other side the flame tough acrylic can bond as a general adhesive to general substrates such as aluminum. So finally, moving on to our capabilities and support. We're definitely priding ourselves in going beyond bonding for these applications. So we want to provide converters and end users with access to our testing and collaboration with our subject matter experts in order to offer the best solutions for your EV battery applications. So on the collaboration front, that includes new product development for custom solutions or for broad solutions that carry across different applications. We offer business development and specification support for emerging applications. Let's say an OEM wants you to come in and help them with a specification on the tape front. You can invite us along and we can help shape their specification and help them test for their parameters to design that for that specification. And then we also offer application engineering and technical support. We have a team of application engineers that are material experts and they know how to best recommend and test for these different materials, which is a good segue for our next spot here about testing capabilities. So we have a strong willingness to test for our converters and end users in this space. We can do the traditional bulk property testing such as peel, tack, and shear, along with environmental conditioning in different temperature, humidity, UV, and chemical environments. But we take that a step further with testing that seems to be a little more unique for this space. So all the flame testing we talked about, we have a flame chamber and we're happy to test that at the tape or the composite level. So if you have, say, again, going back to the silicone foam example, if you have that and you're struggling to find a solution for that, send us material, we'll test which products might adhere to it well, and then we'll take it a step further and do flame testing for it if your customer is requiring it. And just like flame testing, we have a high pot tester where we can test the dielectric strength of the film, the tape, or the full composite level of the construction.
Thank you, Scott, and thank you to all the attendees for your questions. First question we have is, do we advise converters to have a presence at the OEM or the tiers to generate opportunities?
You know, it's always good to have a presence at either one of those. I'm never going to tell you not to have a presence. We have found that the tiers seem to be much more receptive at that presence level because, you know, as being a converter and selling directly traditionally to the tiers more so than the OEMs, not in all applications, I'm going to make some generalities here, but we have found that, especially in this battery space, even though OEMs have been making announcements about collaborations or joint ventures with cell manufacturers, a lot of that work is still being done at the tier level. And that's where a lot of the specification incorporations being driven, but not the ownership of those specifications. So it all seems to be a perfect storm within the tier level, and I would recommend that to probably be the stronger of the two.
Thank you, Mike. Next question. Are there any special tests or equipment converters need to enter this segment?
Well, we just went over the testing capabilities. You know, the unique things that we're seeing here is around the flame testing and the dielectric testing, and we know that's something that's a little more rare right now. As EV battery takes off, that might obviously become more mainstream. But Avery Dennison Performance Tapes has that capability, so that's where you guys can work with us as the material experts, and we'd be happy to test that for you.
Thank you, Scott. Another question that came in, which flame tough product is most commonly used? I think this is referencing what flame tough adhesive.
I'll take that one. So we see a lot of use of our 8065, which you guys aren't going to be able. You're not looking at that big list, but it's our double coated acrylic flame tough material. It's a good balance of cost and performance. And then another area that another product we've seen a lot of interest in is our 8076 differential material. Scott talked a lot about it. It's our differential between a flame tough silicone and a flame tough acrylic, basically allowing you to bond a low surface energy like siliconized foam to something that's a higher surface energy or to a different type of foam, right? So those two materials seem to be our most prevalent that we're currently selling today.
Thank you, Mike. So maybe this one for Scott here. What applications are you seeing the most demand for out of those 7 that Mike went through earlier?
Yeah, so I would say there's 2 that are probably most popular so far with us. So the first being the thermal runaway prevention material bonding. You know, the importance of mitigating thermal runaway is very important, avoiding fires, and that seems to be one where tapes and these mica materials or ceramic fibrous materials or aerogels are needing tape to be processed inside the battery pack. And then I would say the other big application that seems to be most popular is electrical insulation. We see a need for insulating chill plates and other aluminum structures with a dielectric film, and of that virtue being a tape solution. So I would go with those 2, Jim.
Thank you, Scott. And our last question, this is for Scott or Mike. How would someone a converter handle their business across regions? Can we take care of that for them and make it seamless, or how can we handle that?
Well, this space, it definitely lends well to having global capability. And Avery Dennison has that. So the folks on this call are representing Performance Tapes North America, but we also have sibling divisions in Europe and Asia, and they're focused on EV batteries as well. If you're a converter with global locations, it's nice to have that because Asia and Europe seem to be ahead. But we see that with the cell production, these cells are so heavy that they're hard to ship across oceans, so they're localizing everything. So if you don't have a global capability, that's where you can work with us, and we can work something out.
Well, I thought that was the last one, but we have people still here sending more questions.
No, we got about 11 minutes left, according to my somewhat probably slow computer here. So, Jim, do you want to?
Yeah, the question is, what adhesive do you have that bonds to aerogel?
On the aerogel side, our acrylics have actually bonded very well to the aerogels as long as the coat weights are correct. So we haven't had any issues bonding to aerogel materials. We're actually working with a couple different aerogel manufacturers right now on some applications. So any of our flame tough acrylic products seem to work all right in those applications with the aerogels.
Thank you, Mike. And actually, that was our last question. Let me double check to make sure. Yes, that was our last question. So thank you everyone for submitting those. Hope people had good learnings from those. Tomorrow you will receive a post-event email, and in that email will be a feature story that Mike penned titled "Electric Vehicles Are Poised to Take Charge." It's really a great informative piece about trends in the marketplace. Many things will be covered at the beginning of the presentation. So that'll be coming to your email tomorrow. If you look at a copy of today's presentation, please contact your Avery Dennison account manager, and we could have them distributed out to you through one-on-one contact. Probably bring up some more questions and some more dialogue than around the portfolio. But just reach out to your account manager. They'll have a copy of the presentation and be happy to share with you. So once again, thank you for attending. This is a very hot topic, and we're glad that you're able to join us today. And we'll keep in touch with more information about the portfolio as it goes. So thank you, and have a good day.